On the green light. What your title is? Is it superconforming field theories? Is that you?
It's exploring renormalization group flows with supersymmetry.
Exploring RG flows with
Yeah.
supersymmetry. Okay. We've had sort of a SUSY talk every week. So
Yes.
Clay Cordova did an introduction to SUSY, and then Jelma talked about SUSY localization last week. So they've been primed.
Yeah.
So I have your folder, Nadi.
Yes, Maddie, you got a folder. Thank you. Okay, now we're your
I just want to tell you the first 2 weeks have gone great. The lectures were great. The students are fantastic. At least that's what I
Yeah, now the question is, where's Mr. Faulkner? Who sent me an email at 7 o'clock last night. Where am I going? Okay.
Have you seen Tom? Nadi?
No.
He'll materialize at some point. I guess we're ready to get going. Are you ready?
Yes.
Okay. So, happy to kick off week 3. So, halfway through TASI. It was about halfway through week 3 that the exhaustion started to set in for me when I was a student. So, make sure, take care of yourself, do some fun things when you have a moment. But we're really looking forward to the speakers for this week and next week as well. So we're really pleased to have Ken Intriligator here, and he's going to tell us about exploring renormalization group flows with supersymmetry.
Okay, thank you. I'd like to start off by thanking the organizers for the invitation to lecture here. And I'll be giving 4 lectures. The first lecture will be some kind of general discussion about renormalization groups and some of the tools of supersymmetry. The second lecture will be mostly on supersymmetric QCD and Seiberg duality and things like that. The third lecture, I hope to talk about some other 4D n=1 SUSY gauge theories where some other methods are needed and connections to the A theorem. And then in the last lecture, I'm hoping to discuss 5D and 6D theories. And I'll mention some references as I go, but the references are going to be very incomplete. And if you want to see more about the references, I have an old review from the 90s with Nadi from TASI lectures, and so there are some references there. And then there's a terrific newer review by Yuji, who's also here, and so you can look in there for many of the more modern developments. Okay, so some of the motivation, we'd like to maybe understand a little bit better what's the space of quantum field theories. I like to picture the space of quantum field theories as like some big elephant, and we could try to look at different parts of it. And the standard model is somewhere in the space of quantum field theories. Beyond the standard model is somewhere there. And maybe there are some aspects of this quantum field theory that we don't yet understand. And so it kind of, by exploring more of the space, we could build up better intuition. So this is some abstract picture of this elephant of the space of quantum field theories. And when we first meet it, we first meet it by looking at perturbation theory around free field theories. And so we could start off with perturbation field theories. And we know that this doesn't explore the full space of quantum field theories. And that's why people say that there are some theories that are thought to be non-Lagrangian, because perturbation theory around free field theories is something that you can describe with a Lagrangian. And I'll mention, especially in higher dimensions, some theories which you just can't think about that way. But nevertheless, perturbation around free fields does give a lot. And there are also many mysteries still in just perturbation theory around free fields. And so mostly I'll be discussing 4-dimensional theories. And a special aspect of 4-dimensional theories is that there are many Lagrangians that we can write down that are classically conformally invariant, scale and conformally invariant. So we can write down the gauge coupling And we can write down Yukawa couplings. And maybe put a minus sign. Let's use a different letter. And classically, this theory is scale invariant for all values of the couplings G and H and lambda. So we could call these classical moduli, or there's a classical conformal manifold. I'm a little unhappy now about saying moduli for this, because usually I'll use moduli for like spaces of vacua, but we could also think about these as being like expectation values of some background field, so maybe it's not too bad to call them moduli. So these are classically the theory has scale invariance, and a way to say that is that there's a dilatation current, which is basically, so we could write down dilatation current like this, which is classically conserved. But in the quantum theory, this dilatation current is anomalous. And a way that we can describe the anomaly is that the divergence of this dilatation current is the trace of the stress tensor, which classically is 0. But in the quantum theory, the beta functions are non-zero, and that's the statement that this current is anomalous. And so we have some beta function for so basically I'll write something similar to the Lagrangian, but with beta functions as the coefficients. And now, as you know, the sign of the beta function is important. And so if we look at, for instance, the beta function for, say, just a Yukawa coupling as a function of H, it starts off 0 and is positive. Also, likewise, the beta function for the quartic coupling starts off 0 and is positive. The beta function for the gauge coupling, if we're discussing QED, would also be positive. But the sign of the beta function depends on, it can be negative, as you know, if we have non-abelian gauge theories, non-abelian gauge fields. And then it depends on how many matter fields and what representations that we have. But for the moment, let me just say here for the gauge coupling, we could either have it be positive or it could be negative. So in these cases where the beta function is positive, what happens is that as we flow towards the infrared, I can draw some arrows of renormalization group flows as going towards the infrared, the coupling constants go to 0. So maybe I'll just write here. If beta is positive, the theory is infrared free, and the coupling H goes to 0 in the infrared. And in that case, we can ask what happens in the ultraviolet. And at some point in the ultraviolet, the coupling gets strong. And then we need to have some ultraviolet completion. And so there could be a problem in the ultraviolet. There could be, like for the QED, this was what people call the Landau pole, which people worried about at one point. And so there could be a problem in the ultraviolet, or there could be something else that fixes the problem. And so we need some kind of UV completion. Here. One possibility that people discussed a long time ago is that maybe the theory just fixes itself in the ultraviolet. So we could put here, so this is a question mark, we could put here the possibility that maybe it goes back to 0. And for instance, this could happen also in the case of QED. And this is something that people studied on the lattice to try to look at this at strong coupling to see whether or not this can happen. If it goes back to 0, this is what's called asymptotic safety. So we could ask here in the UV, is it asymptotically asymptotic safety with a question mark? And as I'll mention, in some supersymmetric theories, we can argue against this kind of asymptotic safety. We can also look for some examples where it happens, but it's also believed from the lattice that it doesn't happen for many cases, but there are cases where it does happen. Okay, now in this case where the beta function is negative, then the flows are in the opposite direction. So if the beta function is negative, then we say it's asymptotically free in the ultraviolet. So we don't need a UV completion in that case. The theory is UV complete on its own. So let's say here it's UV complete. And in the ultraviolet, the theory is just kind of boring because it becomes a free field theory. So this is what happens in the ultraviolet. Usually I'll draw the flows in the opposite direction. But as we go towards the infrared, the coupling constant gets stronger. And then the interesting question is what happens in the infrared. And so there are various possibilities for what can happen in the infrared. As in here with this asymptotic safety, one possibility is that eventually the coupling constant goes to a fixed point in the infrared. And so that would be an infrared conformal field theory. I'll use this board. So if the theory is asymptotically free, in the UV, then we can ask as we go to the infrared, what do we get? And so one possibility is a conformal field theory where beta has a 0 for some value of the coupling constant. So this is one possibility. And I'll mention a little bit about QCD. This is actually also a subject of intense interest for lattice gauge theorists to understand what's the infrared phase. And so there's some range where this is believed to happen, where you have a conformal field theory. And then there's some other range where something else happens, like for instance there can be chiral symmetry breaking. Where some fermion bilinear gets an expectation value that goes like the dynamical scale cubed. So this is another possibility. In this case, well, I'll mention more about when this is believed to happen. Or the theory in the infrared could just be gapped. In the infrared. So there are all these different possibilities, and in general, in some cases we can argue it's possible to see which is the right one. So for example, there are some cases where you can see a 0 of the beta function at weak coupling, and you can make that coupling parametrically weak, and then you really believe that perhaps this is probably right. These are called Bank-Zaks fixed points, where you can make the coupling constant very weak. And then in general, there's kind of a toolkit of tests for test. In general, often what's done is to guess what's the infrared theory. So we could try to guess the infrared dynamics, and do checks. So a lot of what I'll be discussing in these lectures will be some guesses where we can do a lot of cross checks because of special things with supersymmetry, but the things that we get we think could be more general. So we can see in some cases that there's a conformal window. Like this, we could see chiral symmetry breaking and these gap phases, and there are many kind of cross checks using special things from supersymmetry. So that's what I'll discuss in these lectures, and I just wanted to start off a little bit before discussing supersymmetric theories to discuss non-supersymmetric theories, just to kind of emphasize that these are general questions or general things that we could try to study. I should mention also that there's this $1 million Clay prize to prove confinement in QCD, and so this is still a topic where there isn't yet an analytic proof, and I won't have analytic proofs of the things that I'll be saying. So many of the things that I'll be saying are really based on conjectures with many cross checks. Okay, so. And by the way, if there are any questions, feel free to ask. So one of the ways that we can get some to do some checks is if there are symmetries. And so something that I'll discuss a lot is if we have theories with chiral symmetry, then there's something called 't Hooft anomalies. And if these, I'll discuss what these 't Hooft anomalies are. Did any other lecturer already discuss 't Hooft anomalies? Oh, someone did?
In some context.
Okay. So I'll be giving many examples. And the 't Hooft anomalies are great. Let's just say they're wonderful. When we first meet anomalies in quantum field theory class, they kind of sound like there's something bad about them. And often there is something bad about them, but this is a wonderful kind of anomaly because these are constant on renormalization group flows. Now, if the constant is 0, then it's kind of boring. Because if the constant is 0, then, one way to get 0 is to have a theory that's gapped. And so 't Hooft anomalies get contributions from massless fields. And if there are no massless fields in the infrared, then you get 0  't Hooft anomalies. So if you look in the ultraviolet and you see that your 't Hooft anomalies are 0, then one possibility is that it's gapped in the infrared. If you find that they're non-zero, then it can't be gapped. So let's just say here, if also, I should mention that there are 't Hooft anomalies for discrete symmetries. And if we have non-zero 't Hooft anomalies for discrete symmetries, then the theory might be gapped, but it's also interesting in the infrared. Like there could be a topological quantum field theory in the infrared that's required to match these discrete 't Hooft anomalies. So a lot of what I'll say will be specific to continuous 't Hooft anomalies, but also the discrete case is very interesting. Okay. Oh yeah. I'll mention QCD. Okay. Yeah, I'll get there in just a second. Okay, so just going back to this, perturbing around free field theories, if we want to go beyond free field theories, we could look at perturbing more general conformal field theories. And so now we can have some kind of renormalization group flow here, where we have a conformal field theory in the ultraviolet, and now we can add a relevant perturbation. And here, if the theory is conformally invariant, we can often say use conformal symmetry to put some restrictions on the relevant operators, like these bootstrap constraints and things like that. And so we could study what are the relevant perturbations. So relevant means it's growing as we go towards the infrared. And eventually, just like here with all of these scenarios, we could have these various possible scenarios for the infrared. So we can have some conformal field theory for the infrared. And it flows in, this is the renormalization group flow. It flows into this infrared theory by an irrelevant operator. I'll just put this plus irrelevant in parentheses because as you go towards the infrared, these things go to zero. So this is the universality of the renormalization group flow, is that we can have all of these irrelevant operators that float to zero in the infrared. And I'll often use this kind of general language where this conformal field theory could be free. It could be a gapped theory if the theory gets a mass gap in the infrared. In that case, the conformal field theory is kind of trivial, but I'll just use the same kind of language about flowing between ultraviolet and infrared conformal field theories in a very general sense. And so another constraint is the intuition that renormalization group flows reduce the number of degrees of freedom. So we could imagine that there's some kind of height function here, which is the number of degrees of freedom. And as we flow towards the infrared, we're coarse graining away these degrees of freedom. And so the flows are going down. And so we could have this kind of picture of renormalization group flows as being like flows of water over some kind of mountainous landscape, but it's always going down. And then these infrared, the conformal field theories are like some kind of lakes where the flows can end up. And so this is a general intuition about quantum field theory, not specific to 4 dimensions, but in 4D, this is given by the A theorem, which is that we can use the quantity A as the number of degrees of freedom. So here, if we go back to this statement that the divergence of the dilatation current is the trace of the stress tensor, in a conformal field theory, the trace of the stress tensor should be 0. And it should be 0 when we turn off all of the backgrounds. But when we turn on non-zero backgrounds, the trace of the stress tensor could be non-zero. And I guess probably Jama talked a lot about this for some backgrounds. And in particular, if we turn on a background metric, there could be a contribution which is called C times the Weil curvature squared. And then there's another contribution which is called A times the Euler density. So these are two combinations of the Riemann tensor that are Weil invariant. And so basically these are both, the stress tensor in 4 dimensions has dimension 4, the Riemann tensor has dimension 2. So these are both like Riemann tensor squared combinations that we can make. And this quantity is, C is related to the 2-point function of the stress tensor. And this is the quantity which in 2 dimensions Zamolodchikov showed counts the number of degrees of freedom. And in 4 dimensions, this thing doesn't count the number of degrees of freedom properly, but this quantity A does. So this is the kind of star of in 4 dimensions. And so the A theorem, so let's say in 4 dimensions, there's the A theorem, which is that A in the ultraviolet is bigger than A in the infrared for all RG flows. Yes?
Does A appear in the 2-point function?
Oh yes, thank you. So the question was if A appears in the 2-point function. In flat space, A appears in a 3-point function. Yeah, in curved space, it could appear in even in a 1-point function. Well, this is like a 1-point function in curved space, but so in general, it's in flat space. It's some combination of 3-point functions of the stress tensor. So this statement that the trace of the stress tensor is these 2 combinations. This is in a background metric, and in general, what we could do is we could take derivatives with respect to g mu nu. Maybe I need something like this, and these bring down the stress tensor. And so what this thing captures is I could take functional derivatives of these with respect to the metric. And then I can relate this to a 3-point function of stress tensors. So the 3-point function of stress tensors has two different independent ways that you could write it with the indices. And so these 2 different independent ways are linear combinations of A and C. And yeah, so it's just some property about 3-point functions. In fact, I'm glad that you asked that, because I wanted to mention also another thing that we expect for A is that A should be positive. And this is also for unitary renormalization group flows. And from the definition of A, neither one of these properties are obvious. These are both statements that are things that could be checked in quantum field theory, but they're not. Neither one is obvious. Whereas in this quantity C is obviously positive because it's related to a 2-point function. Okay, so one of the constraints that I'll use a lot, that I'll mention a lot, is 't Hooft anomalies, and then the other one is this idea of the A theorem. Okay, maybe I'll.
I remember if I said until
10:15. Okay, thank you. Yeah. When we look at renormalization group flows with multiple couplings, then we really can see that it could look kind of like this picture of flows of water down some mountainous landscape. And I'll just mention one quick example. In 2 couplings. Just for fun, we could look at 4-dimensional n equals 1 supersymmetric gauge theory with 3 chiral superfields. In the adjoint. And we could add a superpotential, which is so this I is a flavor index. It's an SU3 flavor index. There's a SU3 global symmetry that rotates these 3 adjoints. And we can write epsilon ijk trace phi k. Maybe I'll write it like this. Okay, if we look at the beta function for this theory, for the gauge coupling, at one loop the beta function is 0, and at 2 loops the beta function is positive. And so if we write here the gauge coupling, and now instead of plotting beta functions, I'm going to plot both the gauge coupling and this Yukawa coupling H. And as we flow towards the infrared, the gauge coupling does that. So the gauge coupling is infrared free. If we had 0 Yukawa coupling. And also if the gauge coupling were 0, the Yukawa coupling by itself would also be infrared free. So this looks like a kind of a boring theory. It has these 2 infrared-free couplings. But the fun thing is that these 2 infrared-free couplings can kind of fix each other. And so if they're non-zero, we can have these flows that can end up at a conformal field theory. So there's a line of fixed points. So we can have some flows that go like this to this line of fixed points. And this line of fixed points is in fact the n = 4 theories. SUSY, Yang-Mills. So if we think about the n = 4 theories as being like n = 1 theories, they're n = 1 theories with this superpotential where H should be set equals to G. And so I kind of just like this example because it shows that even if you have kind of multiple infrared-free couplings, you could still have an interacting fixed point once you put them together. So there's some flow in the space of couplings which only along these lines ends up at 0 coupling, but anywhere else ends up at this line of fixed points. And these the n = 4 theories, by the way, have beta n = 4 along this fixed line is 0. We could write it in terms of tau, which you heard about from Clay's lecture. So tau is theta over 2 pi so it's a complex modulus. So these theories are conformally invariant for all values of this complex modulus. That includes both the gauge coupling and the theta angle. And then there's interesting dualities on this, like SL2Z type dualities, electric magnetic dualities, which I'll mention more about these kinds of dualities in the next lecture. Okay, so I wanted to spend a little bit of time on QCD, non-supersymmetric QCD, and then in the next lecture will be mostly the supersymmetric case. So let's discuss n equals 0 non-SUSY QCD, and I'll take the gauge group to be SUNC, and then we can look at different matter representations, and I'll just consider the fundamental representation. So with NF fundamental flavors, so when I say NF fundamental flavors, we could think about this as NF Dirac fermions, or we could, because it's more convenient in supersymmetry, and it's also better to exhibit the chiral structure, I'll describe it in terms of chiral fermions. And so these NF fundamental flavors I'll describe as some two-component fermions. So we have psi alpha, that's the spinor index. They have a flavor index and a color index, and the flavor index goes from 1 to NF. The color index goes from 1 to NC. So these are in the fundamental, and then I'll write psi tilde also with an alpha index. Whenever there's something with an alpha index, there's also the dagger with the alpha dot index. And so I'll just write the things with the alpha index, but there's also the alpha dot that I get from daggering. And these have a different flavor index. Let's call it F tilde. Maybe I'll write the color index downstairs. And so these are in the fundamental of the gauge group. In fact, maybe I'll write here a table. So I like making these kinds of tables. This is something that I learned from Nadi, who's here. So we can make a table of the different symmetries and the different fields and the representations. So the gauge group is SUNC. And then for the flavor symmetries, I'll put some bracket here to emphasize that these are the flavor symmetries. There's an SU NF left. There's an SU NF right. There's a baryon number symmetry. And then there's an axial anomalous symmetry, which I wanted to also include here, even though it's going to be anomalous. So we have these fields that I'll omit all of the indices just to avoid clutter. So these should always be understood as left-handed fermions with the alpha index. So these ones are in the fundamental of SUNC. They're in the fundamental of this SUNF left. They are singlets under SUNF right. So I could write here a 1, but I'll just write a dot. And under baryon number, we can take them to have, let's give them charge 1 over NC, so that a baryon has charge 1. And under this anomalous symmetry, let's say that they have charge 1. And then we also have the psi tildes, and these are in the anti-fundamental of SUNC. SU NF left doesn't act on them. Here I have a choice whether I want to call it NF or NF bar. Usually I call it NF, but maybe I'll just call it NF bar for fun. NF bar. The baryon number symmetry is -1/NC. And under this anomalous symmetry, let's give it charge 1. So these are matter fields and their charges. Okay, I wanted to spend a few minutes on anomalies, and just to emphasize the difference between the different kinds of anomalies. Okay, so as you know, in 4 dimensions, anomalies are related to triangle diagrams. At least in perturbation theory around free fields, that's how we could compute them. So we could look at a triangle diagram, and then we could put currents at the vertices of these triangles, and there are fermions running around in the loop. So for example, we could put the gauge currents here. Maybe I'll just write it as like gauge field lines. So this is the case where I have G as a gauge symmetry. And then we can have the fermions that run around in the loop. So this is the gauge cubed anomaly. And this anomaly has to be 0. Otherwise, the theory is inconsistent. And so that's why here, for instance, there are the same numbers of fermions in the fundamental and the anti-fundamental, because these fundamentals contribute with one sign, and these contribute with the opposite sign. The reason for that is that each one of those vertices has the generator. And so this is proportional to the trace of the generator cubed. And so since the generator for fundamental versus anti-fundamental differs by a sign, this is just, they cancel each other out. There are other solutions to this, like for instance in SU5 you could have a 5 and a 10 bar. So this is some condition for the theory to be consistent. Okay, we could also look at a triangle diagram with a gauge field, and a flavor current. So if I wanted to, I could turn on a background gauge field for the flavor currents, or I could just say I put in the flavor current here. And this is called the Adler-Bell-Jaquif anomaly. And the consequence of this anomaly is that d mu j flavor mu is proportional to FF dual, which I could just also write as like trace F wedge F. Maybe I should just write as FF dual. Okay, so this current is violated by this anomaly. Actually, this current, in perturbation theory, we could fix this current and it wouldn't be violated. But Non-perturbatively, it's violated, for instance, by instantons. So if we integrated both sides of this equation over all of space-time, then in an instanton background, this integral of FF dual is proportional to the instanton number, and this tells us that there's a violation of the charge. So if we integrate this over space-time, the integral over the space part gives the charge, and then the integral over the time part gives like the difference in the charge between time equals minus infinity and time equals plus infinity, and we get something non-zero proportional to the instanton number. So it tells us that the charge is violated by instantons. So this, by the way, can only happen for a U1 current here. Because if we had any kind of non-abelian current here, this would be proportional to the trace of the generator here. And so for anything non-abelian, the trace of the generator is just 0, so we get 0. So we don't even have to bother to check it for the SUNF left and SUNF right. We could just check it for the baryon number and for the axial symmetry. And for the baryon number, we get 0 because we sum over the different fermions running around here in the loop, and the size and the psi tildes cancel for the baryon number. Whereas for the axial symmetry, they add. And so this axial symmetry is violated by instantons. So here we could write, if we want to, we could write here instantons. The instanton vertex. An instanton leads to an interaction that's called the 't Hooft vertex. And this 't Hooft vertex preserves gauge symmetry. It preserves the non-abelian symmetries. It has charge 0 under baryon number. And here we get something that's non-zero. And so that tells us that this axial symmetry is violated by instantons. Maybe I'll actually... Okay, the instanton So the idea of the instanton at 't Hooft vertex is that when we do the functional integral over all gauge fields, we get a sum over all the instanton sectors. The minuses are anti-instantons. Times some at 't Hooft vertex, which is some interaction associated with the instantons. And so this interaction that's associated with the instantons, I like to picture it as some kind of circle. And on the circle there, so this is the instanton. It's the instanton at 't Hooft vertex, but I just label it as instanton. And then there's some fermion zero modes. Psi 1 all the way up to psi NF. And let's put here psi tilde. Up to psi tilde NF. And these are Fermi zero modes. And the counting of these is given by the Atiyah-Singer index theorem. So if you look at from the index theorem in sectors with some instanton number, there's some number of zero modes. And actually what that reproduces is exactly what you get from this ABJ anomaly. And so here there's some coefficient in here which is related to the representation. And that coefficient, we could just read off from here, it's going to be proportional to the quadratic Casimir of that representation. So here, when we compute this, there's a a trace over the generators at each of these three vertices. This one is the flavor one, and so it's kind of decoupled from these other two. So this is the flavor charge, and then this is the trace of the generator squared in that representation. So that's the quadratic index of that representation. And the correct normalization is that it's 1 for a fundamental. And so the fermion zero modes are T2 in the representation of the fermions. So the number of them is this quadratic Casimir in the index of the representation of the fermions. And the normalization of this is that it's 1 for the fundamental of SUN. So here, each one of these different flavors of SUNC give a fermion zero mode, and these ones also give a fermion zero mode. So altogether here, this instanton has charge 2NF under this axial U1 symmetry. So here, this instanton vertex, the actual charge is 2NF. Okay, now we could look at other triangle diagrams. If we want to, we could look at one with another flavor vertex here and a gauge vertex. So flavor, flavor, gauge. And this can only be non-zero if the gauge group is U1. Because again, this is going to be proportional to the trace of this generator here. And so if it's a non-abelian theory, the trace of the generator will just be 0. And this leads to something that's called two-group global symmetry. Which I couldn't resist mentioning, but I won't really discuss it here because it's not going to be a part of these lectures. But if people are interested, I could discuss more about it outside of the lectures. Maybe I'll switch these ones. Okay, finally there's the case of 3 flavor currents. Flavor, flavor, and flavor. So this is proportional to the trace of the flavor currents cubed. And these are the 't Hooft anomalies. So as I mentioned, these are wonderful quantities because they're constant along renormalization group flows. And 't Hooft's argument for why they're constant along renormalization group flows was that suppose that we tried to gauge this flavor symmetry. So if this thing is non-zero, then there's an obstruction to gauging it because trace of gauge cubed has to be 0. So the theory would be inconsistent. But we could try to fix that by adding some spectators that are charged only under that this flavor symmetry, which now we want to promote to a gauge symmetry. And so we could add spectators So this is 't Hooft's argument. And then once we gauge it, the theory should be consistent along all renormalization group scales. And so the spectators will cancel this. They'll cancel it at all scales. And then the idea is that these spectators are decoupled. And so since the theory, since the spectators contribute the same, they're just decoupled from the original dynamics. And so since these spectators kind of just go for the ride, their contribution to the 't Hooft anomaly just stays constant along the whole RG flow, and they're canceling the theory that we're interested in, 't Hooft anomaly along the entire RG flow. And so that's the intuitive argument, that this thing has to be constant along RG flows. And there are other arguments for this without invoking these spectators. But anyway, this is the idea of the 't Hooft anomalies. So these things just go for the ride. So it's a constant along the renormalization group flows. Okay, now let's go back to this QCD. With various NF. So one thing I should also add to this table is that I could add mass terms for these fermions. So let's put here also mass terms. And so the mass term would be, could be, for instance, like M, F, F tilde, psi, alpha, flavor, color, psi, beta, flavor, tilde, color. I'm contracting the color indices, and I'll contract the spinor indices like this, and then I'll add here plus Hermitian conjugate. And these masses here can be complex in general. And so we could see, for instance, that this mass term would violate the baryon number symmetry. It preserves the baryon number symmetry. So the mass term has charge 0 under the baryon number symmetry. It violates the anomalous symmetry by let's give it charge -2, because I could this is the idea of spurions, that I can assign charges to the things that violate a symmetry, and then we could think about the symmetry as being preserved with the assignment of those charges to the coupling constants. So if I assign charge -2 to the mass, these things have charge +1, then it's as if the Lagrangian preserves this symmetry. Actually, the symmetry is broken anyway. It's broken by the anomaly, so that's why there's this charge here for the instant on a 't Hooft vertex, and it's also broken by the mass. But this assigning of charges to the coupling constants that break symmetries is very useful, and this leads to selection rules. And this is something that I think you already saw in Clay's lecture when he talked about the non-renormalization theorem for this theory with Wess-Zumino theory with a cubic. Yeah, so the question was why, if I'm assigning a mass here, why do I say that the UNA is broken? Yeah, so basically I just, if the mass were 0, then we would have classically this UNA symmetry. So if we just look at the theory classically, then we could forget about this instant on the 't Hooft vertex, and we would say that UNA would be a good classical symmetry, and the mass would violate it. And the way that we'll describe the violation, this way of assigning charges to the couplings that violate it, another way to think about this is that we could think about this as an expectation value of some field. And then if we assign charge to that field, then we could think about the symmetry as being spontaneously broken instead of explicitly broken. And the nice thing psychologically about that is that spontaneously broken symmetries are actually still there. You just need to properly account for the fact that they're broken. And the same is true for explicitly broken symmetries if we assign charges. So I'll assign, and that's what leads to these selection rules. So I'll assign charge -2 to the mass. And then, yeah, in the quantum theory, we still have the 't Hooft vertex, which gives this charge. I'm not sure if that addresses the question, but okay. And then for here, I can assign the masses also to preserve the symmetry. So maybe I'll give here a bar for this one because this times this gives a singlet. And maybe since I chose this one to be bar, I'll write this one without a bar so we can get a singlet. And it's, of course, the mass is neutral under the gauge symmetry. Okay, so the mass breaks some of these symmetries. It doesn't break the baryon number symmetry. And so what we can see from that right away is that there can't be any interesting 't Hooft anomalies for the baryon number symmetry. Because I could give a mass to these fermions, and if I give a mass to the fermions, only massless fermions can contribute to these triangle diagrams. And so without even calculating, we could know right away that the 't Hooft anomalies involving the baryon number are going to be 0. So maybe I'll write this here. Trace of U1 baryon cubed is 0. We know it has to be because we could add mass terms, but then we could also just check it. I mean, it's again just because the two contributions cancel. One has baryon number plus, one has baryon number minus. We cube that and add them together and we get 0. Also, there's a 't Hooft anomaly involving just one U1 generator. And these 't Hooft anomalies involving just one U1 generator are here. I could also look at 't Hooft anomalies where I replace the flavor current here with the metric, or T mu nu. And so there are also 't Hooft anomalies for U1 symmetries involving just trace of F. So these are also 't Hooft anomalies. And so for the baryon number symmetry, we can also calculate that. And so we get that this is also 0, as expected, because we could add mass terms. There some non-zero 't Hooft anomalies are trace SUNF left cubed is proportional to NC because only the NC fundamentals contribute to that. We could also look at trace of SUNF right cubed. And here, because I chose to write SUNF right as an anti-fundamental, maybe I'll put a minus sign here. So these are some non-zero 't Hooft anomalies. We could also look at trace of SU NC squared times U1 baryon. So trace of SUNC only gets a contribution from this, and so then we get 1. Okay, sorry, this is trace of SUNF. Okay, the one with SUNC would have been the ABJ anomaly. Okay, so those are the 't Hooft anomalies. Okay, so now we could ask what are the dynamics for various NF? And maybe I'll mention the case NF equals 0 is special. The case NF equals 0 is special for is special. One of the reasons that why it's special is because if we have NF equals 0, we don't have any more these different global symmetries. And so there, in particular, well, let's just say some of the special aspects about it. We can have a theta angle, which we can, whereas for NF bigger than 0 massless, we can rotate it by this anomalous U1 asymmetry. So the anomalous U1 asymmetry is where we do a phase rotation of both psi and psi tilde. And the fact that this is an anomaly tells us that there was this divergence of the current, which was proportional to FF dual. And FF dual, theta is the term, as you know, that multiplies FF dual. And so what happens when you do this anomalous phase rotation is that in the action you rotate theta. And that's a way to see why the symmetry is broken. But because of that, you can rotate theta to 0 by a U1A rotation of psi and psi tilde. Okay, so that's one special thing about NF equals 0. Another special thing about NF equals 0 is that there's center symmetry. By psi and psi tilde. So if NF were 0, we could look at some representation R and R bar, and we could put in these objects as some sources. And they could be separated by some distance. And then there's some color flux that connects these two different sources. And because the adjoint of SUN, if we write it in terms of Young diagrams, the adjoint of SUN in terms of Young tableaus is a tableau with n boxes. And so basically any representation, if we write it as a Young tableau, if its number of boxes is 0 mod n, it could be screened by the gluons. And so the gluons in the Young tableau mod NC. Now, if we had fundamental matter, this colored flux tube could be broken. We could pop out of the vacuum a psi and a psi tilde, and this flux tube will break. And so with fundamentals, let's say with NF non-zero, the flux can break. And the modern way of describing this, which I learned from the papers of Nadia and collaborators, is that this theory has a Zn discrete one-form global symmetry. For NF equals 0. And there are many interesting things to say about this, but since it's not really connected with many of the other things that I wanted to say, and since actually Nadi and Hotat Lam, who are here in the audience, recently wrote a very nice paper about these things, maybe I won't discuss it and just refer you to their paper. So for the case NF equals 0, there are many interesting things that could be said, and they could also be tied into higher NF, but I won't discuss that here. Maybe the one thing I'll say about NF equals 0 is that the infrared theory is gapped for theta equals 0 and generic and something interesting at some value of theta, like perhaps theta equals pi, which I won't really discuss more, except for to mention that the idea is that it's gapped. And the fact that it's gapped means that there are no 't Hooft anomalies, but there's no global symmetry anyway to check, so there are no 't Hooft anomalies to check. Okay, let's look at the opposite limit of large NF. So So if NF is bigger than 11 halves NC, 11 halves NC is where the one loop beta function vanishes. So if NF is bigger than or equal to 11 halves NC, the theory is not asymptotically free. So let's write here asymptotic free with a line through it. And so the theory is infrared free electric. Where G Yang-Mills goes to 0 in the infrared. And it needs some kind of ultraviolet completion. Maybe I'll keep the table. Now, suppose NF is just barely below this bound of 11 halves NC. So let's write if NF is less, let's write it's equal to minus something small, like maybe epsilon here is 1. So in this case, what happens is the theory is just barely asymptotically free. And so if we write the beta function as a function of g, it starts off negative at one loop, but at two loops, actually there's a positive contribution. And so beta of g, it's some minus one piece from one loop and some positive piece at two loops. And so we can find a 0 in perturbations theory. And so this is a conformal field theory. Now we could ask whether or not we should trust this perturbative calculation because there are higher order terms. And one limit where we can trust it is if we look in the limit of large NF and large NC. and just take this thing to be very tiny. And then we can see that in the large n limit, you know that the appropriate coupling is the 't Hooft coupling, which is g squared n. And we could even make g squared n parametrically small. And so these conformal field theories in some cases could be explored in conformal perturbation theory. So there's a conformal field theory that's believed to exist there. And then maybe since my time is, I think, almost or maybe completely up, maybe I'll just plot here as a function of NF. So if NF is above 11 halves NC, it's free. I'm just using this name free electric because tomorrow I'll talk about duals where we think about the duals as some kind of magnetic description. Okay, so here's free electric. Then there's what's called a conformal window. Which starts below 11 halves NC. When you're just below 11 halves NC, this case up here, this is what's called the Banks-Zaks fixed point. Sometimes people call it also Banks-Zaks-Caswell, because Caswell showed that the two-loop beta function was positive. And then there's some NF star, which is the bottom of the conformal window. And below NF star, something else could happen. For instance, chiral symmetry breaking could happen. That's one possibility. And here, this is a subject of study, for instance, in the lattice community, to determine this bottom of the conformal window, what precisely is this NF star. There's some lore based on various things that suggest NF star is on the order of 4 NC. So NF star. So this is an interesting question. Where's the bottom of the conformal window? Did you discuss this in your lecture, Tom?
I said it was really, really hard to do.
Okay. Okay. So this is. Yes. I know. I have a colleague who's one of the fighters. I have a colleague who's one of the people who fights over where's the bottom of the conformal window, not just for this theory, but for other theories. And one of the reasons why this has applications also to some models like walking technicolor and things like that. So maybe I should stop and just say that in the next lecture I'll discuss the analog of this in SUSY QCD. And in SUSY QCD, we know, not as a theorem, but based on many non-trivial cross-checks, where is the bottom of this conformal window. So next time, with SUSY. And maybe just one last thing to quickly mention is that going back to these checks about the A theorem and the 't Hooft anomalies, the 't Hooft anomalies have to be matched here. So this conformal field theory, this conformal window, for instance, has to match those 't Hooft anomalies that I mentioned. And so there have to be massless fields in this conformal field theory that match those non-zero 't Hooft anomalies, like trace SU and F left cubed, for instance. Here in this broken phase, you also have to match the 't Hooft anomalies. And the way that happens is by the pions. They're massless Goldstone bosons, and massless Goldstone bosons can also contribute to the 't Hooft anomalies using the Weston-Witten term. So, for instance, this trace SU and F left cubed 't Hooft anomaly was NC. And so that tells you that there has to be a Weston-Witten term with coefficient NC. This was first written down by Witten. Another point is the A theorem. And so, in fact, the idea of the A theorem was first pointed out in 4 dimensions, was first conjectured by Cardy in 4 dimensions. And the first thing that Cardy applied it to was to try to understand the bottom of the conformal window using the A theorem. And so maybe I'll just steal one last minute and just say that A in the ultraviolet is there's a contribution from the gauge fields. Maybe since I'm anyway stealing time, I should write it down next time. Yeah. So maybe I'll just write here that AUV is bigger than AIR. This doesn't really help with the bottom of the conformal window. This was something that Cardy showed that in principle this could have helped because here there are the contributions of NF squared Goldstone bosons, whereas here the NF dependence is like NF and C from the fermions. And so if NF gets huge enough, these things could contribute too much because this one goes like NF squared, this one goes like NF and C. But Cardy showed that it doesn't really help because gauge fields contribute so much that this doesn't really restrict NF to be anything less. I mean, it has to be less than something that's way up here anyway, and so it doesn't help. Okay, I guess I should stop with that. Sorry to go over.
Forget IRCT, you said this is kind of trivial. What do you mean by trivial?
Sorry, could you repeat the question? I'll repeat the question also. But so the question was IRCFT is being trivial?
The IRCT, you said this series is kind of trivial. Right? But this word. So what do you mean by trivial here? Because in principle, we could have non-trivial topology point of view.
Was the question about the NF equals? So the question was why did I say that the infrared conformal field theory is trivial? And
Forget.
Oh, for gap theories. Yes. Yeah, so right. I think I mentioned this in words, but I didn't really write it down. So the question was, why do I say in gapped cases that the infrared conformal field theory is trivial? And certainly it could be non-trivial. I mean, there's all these SPT type phases, and sometimes non-trivial gapped. Basically, there could be a topological field theory, which could also be required by matching discrete 't Hooft anomalies. And so I should apologize if I use the word trivial. Yeah. So gapped cases could be boring, or gapped cases could also be some very interesting topological quantum field theory. In any of those cases, we would find so many of the things that I'm discussing kind of center around things like A and things like that. But yeah, certainly there could be non-trivial topological field theories, and that could still be interesting. Thank you.
One more. I think you might have mentioned this, but did you say that anomaly arguments tell you that the only thing that can happen as you go down below the conformal window is chiral symmetry breaking? Or are there other options?
There could be other options. So for instance, in SUSY QCD, which I'll discuss next time, there's another phase which is infrared free magnetic phase. And so it's not known in the non-supersymmetric case if there's something like that. The infrared free magnetic phase, I forgot to repeat the question. The question was did I say that these are the only possibilities, conformal or chiral symmetry breaking? So the answer is that there could be other possibilities. What we know from 't Hooft anomalies is that there has to be something with some massless degrees of freedom to match these 't Hooft anomalies. And so in the supersymmetric case, another possibility is that there could be infrared-free gauge fields in the theory, gauge fields and charged matter, and that's the infrared-free magnetic phase that I'll discuss tomorrow. And it's not known if anything like that happens in QCD. Thanks.
All right, let's thank Ken again.
There's brown muck left into my head.
Yes.
Pure gauge theories are very interesting to me.
So we have coffee.
Coffee is over there.
Yeah. Well, there's one of the